So let's talk about the Carnot cycle. What do we remember about the Carnot cycle? Well, you remember that it can be applied to a closed system, or it could also be applied to an open system. But it's the gold standard. You know, it's like the benchmark. Nothing can beat the Carnot performance for a heat engine. Nothing can beat it. And we can also talk about Carnot refrigeration and heat pump cycles, but right now it's a heat engine, and this is the gold standard by which other cycles can be measured. And they won't exceed the performance of the Carnot. So in a closed system, typically it has started with an ideal gas as a review, and maybe you had it trapped in a piston cylinder apparatus, and it went through a couple different processes. So ideal gas in a closed system undergoing different processes. And I won't try and sketch them all, but we had a process from state 1 to state 2. Because it's a cycle, it really doesn't matter where you start in the cycle. But 1 to 2, maybe you have a compression. And then from 2 to 3, maybe you also have a compression. And then 3 to 4, you'll have an expansion. And then 4 to 1, have an expansion. See the pattern? Compression, compression, expansion, expansion. All of these processes are what we call int rev. What does int rev? Internally reversible. No friction. No sources of irreversibility. That's good. Now, when you have the first compression, you have a choice. I can do it either isothermal compression, or I can do it adiabatically. So either I have isothermal compression followed by adiabatic compression, or I have it the other way around. Okay? Let me just tell you it's this way. It's isothermal compression, then adiabatic compression. Then, guess what we're going to have? Expansion. Is it going to be constant temperature, isothermal expansion, and then adiabatic expansion, or the other way? It'll be the first one. It'll be isothermal expansion and adiabatic expansion. How does this make power? How is this a heat engine? Right? So we can explain this on maybe a temperature entropy diagram. Well, and you can also put it on a pressure volume diagram. But on a temperature entropy diagram, or which one do you want to see first? Pressure volume or temperature entropy? Which one? Temperature entropy. Okay. So let's do this. If I have compression and it's isothermal, what does it look like on a temperature entropy diagram? Horizontal. It looks horizontal. It's isothermal, constant temperature. And it's going to be going this way. I'm compressing it. As I compress it, it would normally want to heat up. But because I'm doing work on it, but because I'm trying to keep it at the same temperature, guess what's happening? There's a heat transfer not into the gas, but out of the gas during the isothermal compression. True? So that's a heat transfer out at a low temperature, TL. Then you stop the compression and you do this. You continue that compression, but now it's not isothermal. There's no more heat transfer. We take it away. It's adiabatic. Reversible, adiabatic compression. Temperature is going to go way up. Entropy, the same. So it jumps. So we started at state 1. We went to state 2. Now we go to state 3. This temperature up here is TH. Higher temperature. It's a high temperature. Now we go through straight process from 3 to 4 expansion. Isothermal expansion. Well, that's constant temperature. As I'm expanding, it's doing boundary work, pushing back, let's say, the pace of a piston. And that's an energy transfer out of the gas. To keep it at constant temperature, constant internal energy, I need heat transfer coming in, heating it, while I expand. That's how you have the isothermal expansion. You have to have the heat transfer in to keep it at that high temperature. And then we stop and we expand adiabatically, and you have to stop at the right spot such that when you expand, you land back on state 1. Make sense? How many people could sketch it from memory on a PV diagram? Ideal gas undergoing. 1, 2. Really, I encourage you, right? So what would it look like? Remember on a PV diagram, the ideal gas equation, and then you stop at 1 to 2. That's an isotherm. That's your low temperature isotherm. Maybe I want to sketch it in showing you this is TL. And then you're going to have to jump up to the high temperature isotherm, TH, on a PV diagram for an ideal gas. And when you jump up, you get to 3, and then you expand to 4, and then you jump back down. You're jumping between those two isotherms on a PV diagram. That's a good review. But now we want to talk about using a Carnot cycle, still the gold standard for a heat engine, for an open system. What? I have not a trapped amount of gas in a piston cylinder that's squeezed and expanded and heated and cooled. No, no, no. I have maybe water flowing in a loop from this component to that component to this component. Maybe I have a boiler. Maybe I have a turbine. Maybe I have a condenser. And maybe I have something very unique, but I'm going to call it a pump, but it's really a difficult pump to build. It doesn't exist, but we'll call it a pump. And the flow comes out of one of the devices, out of the boiler and into the turbine. Out of the turbine into the condenser, out of the condenser into the pump, and out of the pump into the boiler. How many people remember something like this? Yeah, right? And we can have a Carnot heat engine where it's these 4 components and the whole cycle is operating to give us maximum performance. The gold standard. Can't be beat. All right? So this, let's label our states now. This 1 doesn't, it's the state of the fluid as it's leaving the boiler and going into the turbine. State 2 is the fluid leaving the turbine going into the condenser. And 3 and then 4 are such. They're labeled like that. Is everything still int rev? It sure is internally reversible. Okay? So when I expand through that turbine, it's a great turbine. It's going to be no heat transfer, Q is 0, and it's going to be reversible. It's going to be an isentropic expansion through that turbine. And when I go through the pump, no heat transfer in the pump, no entropy generation in the pump, isentropic compression or increase in that pump, okay? So that's the same there. It's internally reversible, but we don't have processes anymore. We have components, and the fluid flows through those components. Let's go ahead and see if we can sketch, maybe, on a temperature entropy diagram. Where is all of our work coming out of the cycle? It's coming out of that turbine. Where do we have to feed some back in to make the cycle work? Back into the pump. Where do we feed heat into the cycle? Only one place, that's in the boiler. Where do we reject heat? Typically to the environment, in the condenser. So those are 4 major transfers of energy: 2 heat transfers, 2 work transfers. Okay. Let's go ahead and put this on a temperature entropy diagram. But the trick is as the fluid flows from 4 to 1, heat is being added, but I need a constant temperature heat addition. I need the fluid coming in at state 4 to be the same exact temperature as coming out at state 1. Students see this in thermodynamics 1. They say, impossible. You're adding heat in a boiler, and the fluid coming in and the fluid going out is the same temperature. It is not possible. That's what the students say. But now you passed, you know. And it's due to the change in phase. Exactly right. So can I have a constant pressure boiler? So the pressure is the same in and out, no problem there. Conceptually, I agree. Students typically agree. That's no problem. I can see that. And when I'm adding heat, I'm changing from liquid to vapor, and I'm boiling and boiling and boiling. And so when you come in, you're coming in maybe as saturated liquid. And when you're going out, guess what you go out as? Saturated vapor. If the saturated liquid and saturated vapor have the same pressure, their temperature is the same. It's the saturation temperature for the boiler pressure. So what we do is we come up here and we say, this is T sat at the boiler pressure, T high. And what we want to do is probably put their dome in there. And that's our dome. And it changes phase from saturated liquid to saturated vapor. True? Going from here to here. That's from state 4 to state 1. Some books don't put 1, the boiler output and the turbine input. This textbook does put 1 up here. That's fine. You know what? Because it makes it line up with the TS diagram a little better. But that's a minor point. Now that we expand it through this turbine, what type of expansion? Completely reversible, no heat transfer, hence isentropic from the second law. It's straight down on a TS diagram. What pressure do we come out at? We come out at the condenser pressure. And then from state 2 to state 3, you condense, but you don't condense all the way. You condense just enough so that when you put it through this magical pump in its isentropic compression, S4 is equal to S3. True? So there is our cycle for the Carnot vapor power cycle. All right. Did all that make sense? Let's ask some questions. What is the equation for W sub T? The work per unit mass, lowercase w, that is produced by that turbine. Is it H1 minus H2? Is that what it is? All right. Let me do this, and this will be a clicker question. Is it H2 minus H3 or H3 minus H2 for this answer, for part for Q sub C? Answer A or answer B? All right. Oh, we have such a discrepancy. Why? Let me ask you this. Which enthalpy is higher, H2 or H3? H2. It's higher quality steam. I'm going to have to condense it. I'm going to take energy transfer out, right? And which direction is Q sub C shown on this illustration? Out. It's a positive entity I'm trying to talk about. It's how much heat is rejected. So which one will give us a positive QC? A. Oh. Thank you for participating. Now we'll continue on. What about the work of the pump in terms of the enthalpies? It's going to be H4 minus H3. And the Q of the boiler in terms of enthalpies, H1 minus H4. Okay, make sure you can walk around the system like that. What are some performance measures of great interest? We're interested in the thermal efficiency. The thermal efficiency is the net work, which is the turbine out minus what goes back to feed the pump, divided by the heat in, which only is flowing in the boiler. True? That's the thermal efficiency of this cycle. And then the back work ratio is another interesting metric for the cycle. It says what fraction of the turbine work out has to go back to the pump. As a practical engineer, you want that to be low, the back work ratio to be low. What do you want the thermal efficiency to be? High. As an engineer, you want it to be high. Professor, I really learned stuff about this Carnot thermal efficiency. Is this true? Or is it different? You know, if I calculate it this way, using the equation you've shown right here, will I get the same result if I calculate it that way, where this is my low temperature and this is my high temperature? Will they be consistent? Or will there be a difference? I had great confidence when I did ideal gas trapped in a piston cylinder, but I'm a little shaky about this open system where you have a turbine, a condenser, a boiler, a pump. So is it going to be consistent, yes or no? It'll be surprisingly very consistent. The first time you do it, you say, there must be some magic going on here. How can this happen? Right? That such a simple expression can be consistent with a lot of detailed calculations of getting some enthalpies, calculating the delta H's for the work of the pump and the boiler heat transfer and the condenser and everything else. And it's true. It does. It works. All right. Some people will also see the thermal efficiency written this way. They'll see it as 1 minus Q condenser over Q boiler. What? How did that come about? How can that be true? Well, what did they do here? This is work net divided by Q of the boiler. True? Could I replace work net by Q net? Every day I can. That's a good substitution. Q net is Q of the boiler minus Q of the condenser. True or false? 1 minus Q of the condenser over Q of the boiler. Good? Good. All right. Here is the cleanup of that Carnot vapor power cycle. There's the turbine, there's the condenser, there's the pump, there's the boiler. State 1, inlet to the turbine, 2, state 3, state 4. Here it's shown on a temperature entropy diagram. This whole line right here is a high pressure line, isn't it? This line right here is all the low pressure line. That's the pressure of the condenser. This is the pressure of the boiler pressure. Notice that the pressure at 1 is equal to the pressure 4. Is there any pressure drop in the boiler? No, it's a great boiler. And the pressure at 2 is equal to the pressure at 3. Is there any pressure drop in the condenser? Nope, not at all. Okay, one of the challenges is trying to figure out if you can really make something that can take low quality steam at state 3, let's say X of 3 is maybe 20%, and compress it. Do I use a compressor like an air compressor, or do I use a pump like a water pump? Well, it's in between. And those devices are not readily available. Okay? So this is impractical. So what do you do to make the Carnot vapor power cycle more practical? You do this. You condense all the way so that this becomes saturated liquid coming out of the condenser. If you condense all the way, where does the new state 3 go? It goes right over to here. It goes to the saturated liquid line at that low temperature, right? Then where does state 4 go? If you condense all the way, now it's a liquid, I put it into my traditional pump, everything's good. But where does state 4 go? Does it stay way up here? It stays on that high pressure isobar, and it shifts way down such that I still have isentropic constant S, isentropic increase in pressure through the pump. So it has to stay at this level of S, and there is state 4. Talk to me about the temperature at 4 now that it's shifted. Did the temperature of 4 go up, down, stay the same from where it was when the Carnot? It went down. Think about that boiler. I segment that boiler into zones, right? I heat it a little, heat it a little, heat it a little, heat it a little. Before, when it was Carnot, I started boiling right away. And maybe I had 5% turn into vapor, 10% turn into vapor, 15% turn into vapor, etc. All the way till I got 100% turn into vapor, right? what comes out. But now, what about the first little bit? What happens in the heating process for this practical Carnot known as the Rankine cycle? I'm just heating it up. I'm going from this temperature to this temperature. It's still liquid. I heat it up, this temperature to this temperature, still liquid. I'm climbing up until I get to the point where now I can start boiling. All right. Now that we understand the practical Carnot or the ideal Rankine cycle, what do you think about the thermal efficiency of shifting state 3 over? Do you think it's improved it, left it the same as the, I'm going to call this ideal Rankine. The thermal efficiency of the Carnot, has it increased above the thermal efficiency of the Carnot? Or is it less than the thermal efficiency of the Carnot? And I'm going to try this A, B, C one last time. Let's see if this will work. Do you understand the question? The thermal efficiency of this new modified system where we bring out of the condenser saturated liquid. I'm going to call that the practical Carnot or the ideal Rankine cycle. Is its thermal efficiency the same as the Carnot? Is it better than the Carnot or less than the Carnot? One, done. Now I did hit stop that time. Now when I show results, that's the correct answer. The Carnot is the benchmark. The ideal Rankine cannot be as good as even now the Carnot. Why? We're not bringing all the heat in at the high temperature. We're bringing some heat in at the lower temperature. Let's hit, get rid of that. See that? That's the reason why there's a degradation in performance from the Carnot. Okay? I'm going to go ahead and stop